Hi, everybody. My name is Sean Sinclair, and I'm a fourth-year PhD student at Cornell in the Operations Research Department. Today, I'll be discussing some of our work on sequential fare allocations achieving the NV efficiency trade-off curve. And the paper is also available on arXiv at the link that is listed. Resource allocation problems are ubiquitous across different systems, including food banks, reservation mechanisms, and cloud computing. And each of these different problems or application areas also has its own set of individual challenges. The first challenge is the choice of an objective function. And this really correlates with the desired properties of the allocations, as algorithms can either be formulated to maximize egalitarian welfare or even max-min fairness. Second is the question of the true goal of the principle. And this is kind of whether or not the algorithm wants to try and maximize revenue, as in a cloud computing platform, or efficiency, fairness, reducing latency, or other desirable properties. And the third question is the accepted computational complexity. And this really arises when you're considering indivisible items, forcing algorithms to either use integer programming or randomization techniques. And the last question is the modeling question. And this is whether the algorithm is going to consider an offline model or a stochastic one. And more often, within these mechanisms, the goals between revenue, efficiency, and fairness are often in direct contention with one another. Allocating everything to the individual who will pay the most obviously will maximize revenue. Allocating nothing will satisfy some notions of fairness. And so the primary results of our paper can be summarized by providing an exact characterization of the necessary trade-offs between the last two, between efficiency and fairness, in an online resource allocation problem with multiple resources and individual types. Our work is motivated by a problem and a partnership with the Food Bank of the Southern Tier, which is the local food bank to the Ithaca, New York area, serving 6 counties across the southern border of New York State. In particular, we have been working with them on questions related to scheduling and allocation mechanisms for their mobile food pantry. And we can consider the earlier considerations that I discussed at the beginning specifically for their lens, where for the objective function, they're really focused on a non-monetary mechanism where their primary goals are more for efficiency and the utility for the resources received. The true goal for the food bank is to try and maximize some notions of fairness and efficiency. For computational complexity, we can consider divisible items for simplification, and for the modeling questions, we'll directly consider an online arrival model. As a simple kind of example, here is a map of the Ithaca kind of New York community. And here in the top right, we have the truck, and the truck for the mobile food pantry works out. It starts off at one specific location, and it's loaded up with a fixed amount of the resources and a fixed schedule. Over time, the truck visits a variety of different locations. When it arrives at the first location, here at the top in Cayuga Heights, they observe some certain number of N1 individuals there and decides on an allocation X1 for each of the individuals at that location. The truck then continues to the next spot, observing N2 individuals and deciding on an allocation X2 for those people. This process then continues to the third round and so on. And we consider individuals with a finite set of types, where their type kind of dictates their preferences over the different food resources available from the food bank, whether that be milk or protein or vegetables or fruit, packaged foods, etc. Important in this model is that the allocations are made online with only partial information on the number of people arriving at each of the different locations. However, the food bank does have access to historical data sets, which here you can kind of think of them as histograms over the different demands. And so the key question for this area is how to exploit that information in developing an allocation mechanism. The model that we just discussed has some interesting and unique questions which are addressed in our work. First, the setting is online. And so the question of what even a fair allocation is not so clear cut. And so we tackle this by introducing new fairness metrics, which will be discussed shortly. The second question is efficiency, where we really have to analyze how we can fully utilize the resources that are available to the truck at the beginning, while simultaneously adjusting to the number of individuals arriving across the different rounds. The third question is fairness. So how can we ensure that the mobile food pantry has enough resources to ensure equity across the individuals arriving during the different rounds? Now I'll formally describe the model. So we consider the setting where a principal, here being the mobile food pantry, is tasked with dividing different resources across rounds, where each of the different resources K has a fixed budget BK. At every round, which for the mobile food pantry can be thought of as a distribution location, whether that be a library or a community college, the principal observes a certain number of people at that round of different types, n t theta, corresponding to the number of people at that location t of type theta. The principal then decides an allocation of the resources to give to the individuals of type theta, and the total resources exhausted at the end of the round is equal to the number of individuals of that type multiplied by the allocation that is given. And this process then repeats round by round up until the capital T rounds. In the offline setting, there are established definitions of fair allocations, which has been established by Hal Varian in the 1960s. Specialized to our specific setting, an allocation is said to be fair if it satisfies three different definitions, after ensuring, of course, that it satisfies the overall budget constraints. NV freeness says that across each type and round, individuals of type theta in a specific round prefer the allocation that they were given over the allocation that was given to anybody else. Proportional ensures that individuals prefer the allocations that they were received versus what they would have gotten with kind of a naive solution of just allocating the total budget evenly across all of the people. The third property, efficiency, essentially corresponds to exhausting the total resources. Moreover, an important result that was established in the 1960s is that the optimal fair allocation can be found by maximizing the national social welfare, or equivalently, the convex program called the Eisenberg-Gale program. Unfortunately, all of these definitions that we've listed here critically rely on knowing the entire vector nt theta of the number of people of each type arriving across rounds, which is not true in our online setting. In fact, it's really easy to see that it's impossible to satisfy these three properties simultaneously in an online setting. And so because of this, we're forced to consider approximate notions of fairness when you're trying to develop an online allocation mechanism. And so we primarily consider three different definitions. The first definition we call counterfactual envy, and this looks at the maximum difference in utility between allocations that are made by the algorithm versus the fair allocation in hindsight. The second definition we call hindsight envy, which is completely irrelevant for the optimal fair allocation in hindsight, and instead looks at the maximum difference in utilities for individuals preferring somebody else's allocations over their own. And the last definition is efficiency, which just measures the leftover resources at the end of the different rounds. To get a little bit of intuition behind these different approaches, the first definition for counterfactual envy, you can think of it as the food bank attempting to promise to individuals that they will receive as much utility for their online allocation versus what they should have gotten in the fair solution in hindsight. The second definition seems also a little bit natural, but it is trivially in order to get a hindsight envy of equal to 0 by just allocating nothing across all of the different rounds. But you can also show that in certain situations, and especially for our algorithms, all of the kind of trade-offs between the envy and efficiency can also be formulated with hindsight envy as well. And the last definition for efficiency is obviously important for the food bank because it measures the leftover resources from the allocations that are made by the algorithm. And so the main contribution for our paper can be summarized by this one kind of graph here. In particular, we show that there's kind of three distinct regimes for counterfactual envy and efficiency pairs. The first region is this region to the left, which shows that counterfactual envy smaller than 1 over square root of t is impossible. The second is this region below the curve, kind of xy is equal to 1, which shows that envy and efficiency must be inversely proportional to one another. And the last region is an achievability result on the top right, which shows that our algorithm that we've developed is able to achieve any given point on this particular curve. In particular, a little bit more formally, we show that under mild regularity conditions, we have these three different properties. This first property is this kind of statistical uncertainty principle that says that any algorithm has to suffer a counterfactual envy larger than 1 over square root of t. The second property is this region below xy is equal to 1, which we call the envy efficiency uncertainty principle that says that counterfactual envy and efficiency must be inversely proportional to one another. And lastly is an upper bound by our algorithm, which is kind of characterized by a parameter LT that you can give to it, showing that our algorithm is able to achieve any given point on that specific curve. The way that the algorithm works kind of uses a two-phase approach, and it's parameterized by the given value LT for the desired bound on the counterfactual NV. The first property is we use prediction for the future arrivals, and the second key concept is optimizing the Eisenberg-Gale program. And so the way that it works is first we use concentration in order to generate overestimates for the number of random variable for the number of people of each type data arriving at each of the different rounds by its mean plus a confidence term. Second, in the original Eisenberg-Gale program that we saw the optimal solution satisfies with the true random number of people substituted in, we replaced those values in the optimization problem with these overestimates that we got from using the confidence intervals. And we solved that Eisenberg-Gale program in order to get a pessimistic allocation, which we denote as X lower. Then once we're given X lower, to some extent, we set the upper threshold allocation to be the lower threshold plus the desired bound on the counterfactual NV. And using some new techniques for the concentration and sensitivity analysis for the optimizers of the convex program, being the Eisenberg-Gale program, we're able to ensure that with high probability, the optimal fair allocation in hindsight is indeed above our lower threshold allocation. And this is kind of a key technical contribution, and it's different from some of the prior literature because instead of doing sensitivity on the optimization or the objective function, we are doing sensitivity analysis for the actual optimizer. And these two allocations, the lower threshold and the upper threshold, are used as guardrails for the algorithm. And so when deciding an allocation in a specific round, at every iteration, the algorithm does a simple check. First, it checks if there's sufficient budget in order to allocate this lower threshold to an optimistic estimate of all of the future demand. And if we're able to guarantee that, we know that we're okay. We can kind of allocate according to the lower threshold to everybody arriving in the future. And so we allocate according to the upper threshold. And if we're not able to establish that, then we allocate according to this lower threshold. And in the analysis, and also for some of the techniques for showing that our algorithm achieves every single point on this curve, you can kind of interpret this algorithm by doing the following. First, we kind of generate these lower and upper threshold allocations. And to some extent, by kind of fixing these specific allocations, we're accepting a counterfactual NV loss of the given parameter of LT. And once we've kind of accepted those specific loss in NV, the algorithm changes its interpretation and instead tries and optimize or minimize the waste. And in the analysis, we kind of consider a coupling argument between an algorithm which is forced to play within these guardrails to a profit which is trying to minimize the waste. And for more details on this analysis, you can look at the paper. From this, we also do a numerical comparison of the different algorithms for a variety parameters of LT. In particular, we compare our algorithm with an LT value of t to the -1/2, t to the -1/3 in green, and a fixed threshold algorithm, which you can interpret as using LT is equal to 0. In the plot on the left, we have a comparison of the counterfactual NV as we vary the number of rounds. And of course, we see that when we pick a smaller value of LT, then the counterfactual NV is also going to decrease. In the middle plot, we show the efficiency, which again highlights that when you pick a larger value of LT, then the efficiency necessarily also has to increase as established by this NV efficiency uncertainty principle. And in the plot on the right, we also have a comparison of the ex ante NV, which takes the expectation outside of the maximization. And this is a numerical comparison of the algorithms on a 2019 data set inspired by the Food Bank of the Southern Tier from the partnership that I discussed at the beginning. On top of these numerical comparisons, we also have these radar plots established, which shows that there's a more nuanced discussion between the different relationship of these different metrics, especially in an online setting. And so in the radar plots, we're able to compare the different algorithms' performance on efficiency, a measure of proportionality, its national social welfare objective, its hindsight NV, as I discussed at the beginning, the counterfactual NV, and also the ex ante NV. And for more information and also more discussion on the kind of trade-offs between these different metrics, feel free to look at the paper on arXiv. And so just to kind of summarize the main contributions of our paper, you can really just think of it as this one picture right here, where we show that there is a necessary trade-off between counterfactual NV and efficiency along these different curves here. And so the first property is a statistical uncertainty principle, which shows that the counterfactual NV needs to be larger than 1/√t. The second property says that efficiency and envy need to be inversely proportional to one another. And the last part is the region on the top right, showing that our algorithm is able to achieve any trade-off on this curve. So thank you for watching. And for more information, please look at the paper on arXiv.